Everything is saying it's 0. Algebra says it's 0. Calc 1 also says it's 0. It's 0. That's what the work is. It's fucking 0. Okay, what's up, Calc 4? So, the reason why you take out these classes is because you want to learn tricks to do math faster than what you've normally been doing. Now, you could, right, we want to find the work. I should probably say that. Find the work. Okay. So you want to find the work, and we have this force vector, and then obviously we're going to travel around some path. Maybe it's like this, right? And we end back here. Right? It could be this path, right? Like this could be where we start and travel, you know, counterclockwise, and we end up here. And this would tell you, what would this tell you? Tell you the work, right? And let's say this field. I don't even know what this field looks like, but let's just say the field looked like this. So like the field had these force vectors all pushing up in this one direction. I actually don't know what the field looks like, but I'm just telling you. Just imagine what this is, right? And this is what we want to do. This is the idea of calculus. Maybe you start driving your car here, and you're driving against the wind, and then maybe the wind is in your favor and then not in your favor, and you want to know the amount of energy expenditure that is, right? The amount of work. Okay. So this is why we learn calculus, to do things like that. But I'm going to tell you, if you do this problem, do it out the whole way, you're going to realize that the work is equal to 0. And what you can do is you can use Green's theorem. So you can use, I'm going to call it GT. And what GT says is, okay, so we got the single integral going in this counterclockwise path over some curve, right? And it goes P dx plus Q dy. And if you're not familiar with this form, you could also write it as what? You could write it as f dot dr. Okay, so this is like line integrals right here. But then what Green's theorem says is, okay, if that's true, then you could also say this. Now, Green's theorem does have the assumption that this force vector P and Q they have continuous partial derivatives, right? So that's the assumption. But instead of doing these single integrals, you can convert it into one big integral as long as what? For any positive counterclockwise closed curve. So you can go from a single line integral to a double integral because you're integrating this domain, right? So instead of a C standing for curve, it's not integrating along some curve, you're integrating along a domain, which is, a shape, closed shape, right? And Green's theorem goes like this: Qx minus Py. So this is Green's theorem. Now, like I said, you can do it this way, and you'll find out after doing 5 hours of derivatives like I did, like an idiot, you see that this all comes down to 0. But what you should use is use your brain and think about, what if the field is conservative? Okay, so I'm going to say if the F, so if the force field, right? If the F is conservative, then what did we learn last chapter? Well, then F is equal to some gradient times some function. I mean, the gradient of some function little f. That's true, right? And if this is true, then what else is true? Well, then we know that f dot dr, well, that is going to be the same thing as b to a. See, b to a of f dot dr. Okay, look, I said f del f del. See, like they're equal. And then this is what? The fundamental theorem of line integrals, which is fb minus fa. And then this is how you would do it. But what if we said it's a positive counterclockwise closed curve? Well, that means that b and a are the same point, right? You start at A, you go around in that giant loop that I did, and then you end up at B, but they're the same point. The start and end point is the same thing. So if the start and end point, whatever function it is, it doesn't even matter, but if you evaluate the same point twice and then you subtract it from each other, the same thing minus the same thing is equal to 0. So that's really nice, right? Okay. Now, all we gotta do is go back a chapter, like I've been saying, and check if this field is conservative, right? So let's do it this way. So we can say, usually say exact / conservative if what? Okay, we say if P with respect to Y is equal to Q with respect to X. And then look at this. If we apply that logic into here, would that mean that this double integral is equal to 0, right? So P with respect to Y, Q with respect to X, if you take that and then you put it into this integral anyway, this thing would be double integral 0 equals 0, okay? Then, I'm going to say then Green's theorem says work is equal to 0. Okay, so that's true. Now, like I said, all we got to do is actually just take these derivatives with respect to those certain variables, and everything is true. This is a lot easier to write out. This makes you also seem cool if you're writing out things like this rather than actually just doing these little derivatives over and over again and then trying to integrate some really large thing, right? I mean, this is much easier to do too. Okay, so P, what is P? P is y squared minus x squared over x squared plus y squared squared. Okay, what's Q? Q is, by the way, yeah. Let me write it like this. Sorry, I made a minor mistake. This is P, this is Q. So this is, I just mixed up the order real quick. Everything else is correct, don't worry. P, okay. So this is P, right? I'll write it right here, P, Q. And don't forget we factored that thing out. That's just how the problem was because I wanted to try to scare you a little bit. 2xy x squared plus y squared squared. So, like I said, I'm just going to take these derivatives, and if all of that is true, then I get to walk away without doing that much math, and that's what I really want to do. Okay, so Q with respect to X, let's do that. So, oh, look at that. It's going to still be a decent amount of calculus, but it won't be as bad as we think it is. X squared plus y squared, quotient rule, right? So bottom squared, so bottom is what? It's this, so we're going to square that, so it's going to become to the power 4 now. And then it goes bottom to top, top to bottom. So bottom is x squared plus y squared squared. And then derivative of the top, but with respect to what variable? You take it with respect to x. So it's negative 2x. So bottom to top, top is what? Y squared minus x squared. And then derivative of the bottom, so you take that derivative with respect to what variable you take with respect to x. So it becomes 2x squared plus y squared. With respect to x, remember, 2x. And let's write this out. Let's just literally just drop this down as two different fractions. Okay, so it's going to be negative 2x divided by x squared plus y squared squared. If you're confused what I did, I've just broken it up into two fractions. There's x plus y squared here, multiplied by this negative 2x, and there's x plus y squared to the power 4. Just canceled two of these top ones out. That's all I did, okay? Then this one is going to be... Now, I just want to say real quick that you see that there's a negative 2x parenthesis y squared minus x squared divided by x squared plus y squared parenthesis 3. It should be, instead of a 2 in the front as a coefficient, it should be a 4. It's a minor mistake on my part. However, the theory still holds. If you don't believe me,
you should put all of this into a derivative calculator and see for yourself. And later on in the video, I will correct the mistake. Unfortunately, for this clip, you'll have to do.
Okay, so bottom to top, x squared, y squared, squared. The top with respect to what variable? With respect to y, so it becomes 2x. Oh, look at that. I mean, it's already almost matching. And remember, there's going to be a little bit of a what happening here? The negatives, right? There's some negatives here, so don't think I'm wrong yet. Just let's complete the problem and then see what happens with these negative signs and see them all cancel out. So next one is bottom to top, top to bottom. So top is 2xy, then the bottom going to be 2 times. That's a multiplication, dotted, right? X squared plus y squared, 2y. Okay, let me write this bigger. Okay, so that's all true, right? Let's write this down a little bit differently. Now it's going to be 2x, x squared plus y squared, squared, minus what? 2y, 2xy. What happens here? Times the 2, it's going to be negative 8xy squared. And there's x squared plus y squared here, so let's just keep it out. And that's x squared plus y squared cubed. Okay. So this is true, right? These are the derivatives. And, okay. So this is q with respect to x, p with respect to y. And then we can see that this is y minus y squared minus x squared. Now right now we can't do that much with it. And I did say if they're equal, the field is conservative, then all this is true, right?
Due to that minor error I had earlier, I'm going to redo the rest of that problem, but it'll be done on this whiteboard. Everything on the whiteboard is correct, and you'll see that everything will cancel out to 0 at the end, and we'll have a double integral of 0, which equals 0, and therefore the work is 0.
Okay. Let me move it right in here, so now you guys can see it. Okay, so I'm arguing that these things are the same thing. I'm going to try to make them look like the same thing so you believe me a little bit more. Okay, they both, now first off, they both have the same right here. So, I mean, they both have the same denominator. I mean, and they both have this same, and they have x squared plus y squared, x squared plus y squared. The only difference is right here, right here, right here, right here, right here. Except these are very similar. This is just a negative one here. Okay, let's go through this. So dq dx. Let's just put this into two fractions. So it'll be negative 2x, x squared plus y squared cubed. 4, 1, these are the same thing. You can cancel. Okay. Minus what? Minus 4x, x squared plus y squared. Okay. You can cancel that out. Y squared minus x squared. And then this will be what? Oh, by the way, this one should be a 2. This one's going to be a 3. Right? Because we can only cancel out 1. Yep, 1 second. I knew, minorly copied this down wrong. There's a 2 and 2 here. That's why that was a 2. I knew something was up. Okay. Everything's correct. Don't worry. I just copied something down wrong. This is good. Okay. How about this one? I think the same thing kind of happens here. 2x, x squared plus y squared, squared, minus 8xy squared, and then x squared plus y squared cubed. Okay. So what we need to do is rewrite this one. Negative 2x, x squared plus y squared minus, and it'll be plus 4x cubed, x squared plus y squared cubed minus 4x y squared x squared plus y squared cubed. Okay, so I'm saying that these things are equal, right? That's what I'm saying. So equal. If this is a negative here, and this other side is positive, then if I add it to the other side, so if I add them they're equal, right? So we have dq, why do I keep writing dq dx equal to dp dy, and then I'm saying that if I go like this, which is, I'm literally writing Green's theorem right now, dq dx minus dp dy is equal to 0. So I'm going to make it into this form. This is literally Green's theorem right here, the integrand for Green's theorem. So it's going to be what? 4x x squared plus y squared squared, and then 4x cubed plus 4x cubed, actually it'll be minus, so I'm going to put everything on this side, minus 4x cubed, x squared plus y squared cubed. Then I'm going to add this one to this one, so it's going to be minus 4x y squared x squared plus y squared. So I'm arguing that this is equal to 0. Let me write this. Equal to 0. I'm arguing this is equal to 0. Okay? What if I times this out? If I want everything to the power of 3. So I go 4x x squared plus y squared minus 4x cubed minus 4x. This is a cubed. No, it's a squared. My bad. It's a squared. Squared. All over x squared plus y squared cubed. I'm arguing that this is equal to 0, right? Okay. Great. This should be equal to 0. Okay. 4x cubed. 4x cubed. 4x times y squared, 4xy squared. 0 over x squared plus y squared equal to 0. If you didn't see, yeah, there you go. Right? This, everything up here in this numerator cancels out. So if the numerator is equal to 0, then the whole thing is equal to 0. Yeah, right here, what did I say? Right? I said, if this is true, if all this stuff is true, the work is equal to 0 because our integrand will be equal to 0, and if our integrand is equal to 0, then our integral is equal to 0, right? Everything is equal to 0, the work is equal to 0, the field is conservative, Green's theorem says it's equal to 0, the fundamental theorem of line integrals would say it's 0, everything is saying it's 0, algebra says it's 0, Calc 1 also says it's 0, it's 0. That's what the work is, it's fucking 0.
Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.